Hello, in this video we're going to look at minimum and maximum problems, which is the final application of calculus for this course. So the motivation for this section would be, what is the maximum value of fx equal to 5 minus x squared? And to do something like this, you could probably use your knowledge from pre-calculus. We know we have a parabola opening down, it's got a vertex at 0 and 5. And so from that, if we give it a rough sketch, well, we'll see that the maximum value is right up at the top. The maximum value is happening right here at the vertex. But what if somebody asks you to do this, the maximum value of fx equal to 4 minus x squared plus x cubed? Well, this is now a degree 3 polynomial. It's going to be much more complicated to graph, and it's harder to figure out where the maximum value would be on a more complicated function like this. Now, we do have a lot of tools ready to work on these types of questions. So if we recall the first derivative test is used to find relative minimum or maximum. The extreme value theorem states that the absolute minimum or maximum occurs somewhere on the interval a to b, and so together we can use these results to maximize and minimize problems. So let's look at our example here, and we're going to look at the specific domain -5 to 0. So our first step, like questions we've done before, would be to find the derivative, which will be 2, 4 minus x, and then we'll use chain rule to get a -1, plus 3x squared. We're going to want to set this equal to 0, so first we should probably expand. This will give us -8 plus 2x plus 3x squared. So we have 3x squared plus 2x minus 8. So if you do a little bit of factoring work, you'll get 3x minus 4 times x plus 2. And you can check that that factoring is correct. -4 times 2 will be -8. You'll get 5x, or 6x, sorry, minus 4x, which will be 2x, and then you'll get 3x squared. So we set this equal to 0. And we get x equal to 4 over 3 and x equal to -2. So on a sign diagram, we would have the following. We've got -2, and we've got 4 over 3. Pick a number bigger than 4 over 3, say 10. We're going to get positive, negative, positive. So the graph is increasing, decreasing, increasing. Now you might think to yourself, well, that means the maximum value is over here somewhere because it keeps increasing and increasing and increasing. But the domain is very important. We're told to look from -5 to 0. And so the way I often do this is I draw over here the domain. Well, -5 will be less than -2, and then 0 is between the two somewhere. So there's my domain, which means all of this gets crossed off because it is not an element of the domain. Which means that we're not looking over here for a maximum because the function is not defined there. It's only defined between -5 and 0. Instead, we just look in this portion, and here it very clearly shows us that the maximum is going to happen right here. We are going to have a relative max. And again, this 2 is maybe moved over a little bit. We should maybe move this over just so it looks a little bit nicer. We've got it right here. Here's our value 2, and so we've got a rel max. Okay, so let's go ahead and calculate f of, oh, sorry, that should be -2. Let's go ahead and calculate f of -2. So f of -2, 4 minus -2 all squared, -2 cubed. So that'll give us 6 squared minus 8, so that will give us 36 minus 8, so 28. So there's our maximum value. The maximum value the function takes on is 28. Now, many of the examples we're going to be looking at start with words versus functions. So let's look at this example here. An oil can has to be made in the form of a right circular cylinder to contain 16 pi inches cubed of oil. What dimensions of the can require the least material? So if you notice, there's no formula, there's no equation, no function here for you to do calculus on. That step of do the derivative and set it equal to 0 is going to take a little bit of time to get to. And in particular, we're going to want to follow these steps for finding the max and min. So step 1 is we need to draw a picture. We need a picture if we're going to understand the word problem, and we're going to want to label it. Step 2, we're going to want to identify the variable to be optimized. What variable are we trying to maximize or minimize? We're going to want to develop an equation involving it. Step 3, we often need to develop another equation to substitute and eliminate for extra variables. This is similar to the related rates method. Step 4, once the primary equation is in terms of only one variable, and this is very key, we need to have it in terms of only one variable. For related rates, we could sometimes get away with 2 variables, but for this one, you must have it in terms of only one variable. Then you differentiate and set equal to 0. Step 5, you're going to test your solution with a sign diagram. Step 6, you're going to identify the domain, and then step 7, you're going to answer in words. So let's try this oil can example here and see if we can follow these steps. So step number 1, we should draw a diagram. So a right circular cylinder means a cylinder. Circular means the bottom is a circle, and right means it's straight up and down. So we'd have something like this. Here's our oil can. We want to add some labels to it, so oil cans have a height, and of course they have a radius. This is step number 1. Now step 2, what are we trying to maximize or minimize? Are we trying to maximize the height, the tallest can around, or the radius? Well, no. They want the least material. So they want the surface area to be as small as possible. Material is talking about area. So what is the surface area of a cylinder? Well, hopefully we remember our formulas. There's going to be 2 pi r squared for the 2 circles on top and bottom, and then 2 pi r h for the lateral, the part around. And so this formula is what we want to minimize. Very important we know what we're trying to do. We want to minimize this formula. But notice there's r and h. So step 3, we need to come up with another equation. And in particular, we are given the volume of the can. It's supposed to be 16 pi inches cubed. So we know something about volume. So what is the volume of a cylinder? Well, it's pi r squared h. And we know that that's supposed to be 16 pi. So 16 pi is equal to pi r squared h. We can cancel those pi's. So 16 equals r squared h. Now we're trying to eliminate one of these variables here. You could eliminate r squared by dividing this by h and then plugging it in, but there'd still be an r over here. So I think it's easier to eliminate the h here. There's only one h, so I'm going to isolate for h and then eliminate it. So that would give me h is equal to 16 over r squared. And now I'm going to take this and plug it in for h. So that's going to give me surface area is equal to 2 pi r squared plus 2 pi r 16 over r squared. Now when you're doing this, you definitely want to have your equation simplified. You don't want to have extra things like this because this would require a product rule. So you always want to simplify before you do calculus. So we're going to get surface area is equal to 2 pi r squared times or plus 32 pi over r. So this is what we want to do the derivative of, and notice it's in terms of only one variable. So let's go ahead. This will be step 4 we're into now. So we're going to find the derivative. And to help differentiate between this and the related rates, I always use the prime notation for this and the DDT for related rates, just so you can keep the word problems separate in your mind. So this will be 4 pi r plus 32 pi, well the r is to the negative 1, so it's negative 1 r to the negative 2. Now we want to simplify this because eventually we're going to want to set it equal to 0 and draw a sign diagram. So this is minus 32 pi over r squared. We've got to make these common denominator, so we get 4 pi Again, I'll do this here in another color. So this is over r squared, and then we've got to multiply by r squared. So we're going to get r cubed minus 32 pi over r squared. So we'll keep on trucking here. This is going to give us 4 pi is in common, r cubed minus 8. And hopefully you remember your difference of cube formula, because it's coming in handy right about now. R minus 2, r squared plus 2r plus 4 over r squared. Alright, so this is our derivative. It's simplified, it's been factored, it's good to go, so we can draw a sign diagram over here. We've got this portion never gives you any roots when you're looking at doing the difference of cubes or sum of cubes formula. So we've only got r equals to 2 from the numerator. And then of course you've got r equals to 0 from the denominator. Pick a number bigger, you're going to get, oh, and this is even, positive, negative, negative. So decreasing, decreasing, increasing. And again, it might be tempting to say, well, maybe there's a maximum or minimum or something going on over here, right? What are we trying to do? Well, we're trying to find the minimum. Maybe it decreases here to a minimum. It looks like there's a minimum here, but maybe there's a minimum over here. But we have to think, what's the domain? And this is a sign diagram in terms of r. This is r equals 0, r equals 2. Could r be negative? Could you have a negative radius on a cylinder? Well, no, of course not. R must be greater than 0. So here we draw that, we cross all this off, and this part is not in the domain, which means r equals to 2 is the rel min, and of course absolute min as well, because it's clearly the minimum value we would have. Now what they asked for in the question was the dimensions of the can. So we have one of the dimensions r, we need the other dimension. Well, we had an equation for h, if you look back, h was equal to 16 over r squared. So h will be 16 over 2 squared, which is 16 over 4, so 4. And so our final, this here, again, just to keep the steps, this would have been step 5 here with the sign diagram, and this would have been step 6 with the domain. So we're on step 7 here, we're going to answer in words. We could say the dimensions are r equal to 2 inches, h equal to 4 inches, making sure you use the units that they gave you in the question. Now if you noticed, we had to use an important formula, the volume and surface area of a cylinder here, so we're going to review some of our important formulas with a few questions. So what is the volume of a sphere? Well, the answer for this one is D, 4/3 pi r cubed. Remember, it's going to be cubed because it's a volume, and the 4/3 is there because, well, go Google it if you're interested why the 4/3 is there. It's an interesting story, but that's the volume of a sphere. What is the volume of a cone? Well, this one, hopefully you remember the trick. There's going to be a 1/3 because it's like a triangle. That's our memory trick. And it's going to be 1/3 pi r squared h, b. How about the volume of a cylinder? Well, cylinders and cones are related. They're circles that have been pressed up a height of h, and a cylinder doesn't have the 1/3 in it. So the answer for this one is D, pi r squared h without the 1/3. What is the volume of a box? Well, a box is just length times width times height, no pi involved, so the answer would be A. What is the surface area of a sphere? Well, this is one you can use a bit of a trick on. You can take the derivative of the volume, only works for spheres, but it works here. So the derivative of the volume, the 3 will come down and cancel with the 3, so you'll have 4 pi r squared. So using that memory trick, we get B. Surface area of a cylinder? Well, we just looked at this one in the video, so hopefully it's fresh in your mind. The surface area of a cylinder will be 2 pi r squared plus, was it pi rh or 2 pi rh? 2 pi RH. Remember, this here is the circumference, and then this is the height. The area of a semicircle. Ooh, tricky question. What's the area of a semicircle? Well, remember, a whole circle is pi r squared. So if we cut it in half, we got to cut our number in half. So pi r squared over 2. What's the perimeter of a semicircle? Well, a full circle would be 2 pi r. You'd think if you cut it in half, you'd just get pi r. But you've got to remember that if you cut it in half in a semicircle, now you have this extra portion here. So this is pi r. If this is r, this is another r, so this is 2r. So it's pi r plus 2r. So let's try another problem here. A rectangular sheet of metal has a perimeter of 30 centimeters and is rolled into a cylinder open at both ends. We've got another cylinder problem here. Find the dimensions of the rectangular sheet so that the cylinder has a maximum volume. Alright, well, we've got this rectangular sheet. And we've got a, well, I guess we should label it maybe with a width and a height. It's supposed to be rolled into a cylinder open at both ends. Okay, so it'll be a cylinder. This will still have the same height h, but I guess this will have a radius r. And what are we trying to do? Well, we want to maximize the volume. And again, these should make sense. If you were making a cylinder out of a sheet of metal, if you were working at a company, you wouldn't want to make the smallest cylinder possible. You'd want to make the biggest cylinder possible so that you got the most bang for your buck, the biggest cylinder to hold whatever substance you needed out of this piece of metal. So the volume of the cylinder, which is pi r squared h, this is what we want to maximize. Alright, so again, two variables there, so we need to do a little bit of work. Well, we know something about the perimeter. So the perimeter would be equal to 2w plus 2h based on my variables. And so 30 would equal 2w plus 2h. We could divide everything by 2, so 15 would equal w plus h. Well, I guess that would allow me to sub in for h, but then I'd still have an r here. That's not great. I need to, again, have only one variable in the end. That's my goal. So I could do that, but then I'm going to need to get rid of r. And drawing this r is a bit of an extra variable here because the width, if you think about it, will be rolled into the top of this cylinder. So we could make another formula here based on width. Because if we think about how long this is around, well, that would be width. And the distance around a circle, of course, is the circumference. So we know that the circumference is equal to w. And we also know circumference is equal to 2 pi r. 2 pi r. So we could say that radius is equal to w over 2 pi. Just finishing off my equation over here, I've decided now to sub as h equals to 15 minus w. So if I take this formula, I'll get rid of the h and end up with the w. If I take this formula, I'll get rid of the r and end up with the w. So I'm going to have all w's, which is fantastic. So let's do that now. We're going to get volume is equal to pi w over 2 pi squared 15 minus w. I now have an equation with only w. Now, like I've mentioned before, it would be a good idea to do some algebra here and clean this up before you do calculus, unless you love the chain rule and the product rule. But I am getting close to the calculus step. So this will be, well, w squared over 4 pi squared, 15 minus w. I can cancel one of the pi's. So volume would equal 15, well, I guess I don't need that bracket there. 15w squared minus w cubed over 4 pi. And again, I probably don't want to use the quotient rule, so I should get rid of that denominator and get volume is equal to 15w squared over 4 pi minus w cubed over 4 pi. So there we go. I've got a nice, beautiful equation. So let's put that over here, and we're going to do some calculus on it. So I'm just going to make some space. V prime is equal to, well, I'll get 30w over 4 pi. Again, we have a denominator that is just a regular number, so it's a constant. We don't have to do the quotient rule there. Minus 3w squared over 4 pi. We'll combine those up to give us 30w minus w squared, 3w squared over 4 pi. Factor a 3w, giving us 10 minus w over 4 pi. So we can draw a sign diagram with that information. We've got a 0 at 0, we've got a 0 at 10. Pick a number bigger than 10. We can't say 10 this time. Say 20. And it'll be negative. So negative, positive, negative. So it is decreasing, increasing, decreasing. But we know that the domain of w is not all real numbers. The width couldn't be negative. So w must be positive. So here, we're going to cross this off. Again, if you had a rectangular sheet that had a negative width, well, you wouldn't have a sheet. That would make no sense. So this is not in the domain. That gives you 0 to 10 and then 10 onward, and you can clearly see here we're going to have our rel max. Now what was the question asking for? Well, they wanted us to find the dimensions of the rectangular sheet. So we found w equal to 10. That's great. We also need the other dimension, which would be height. So we know that height was equal to, based on our equation, 15 minus w. So 15 minus 10, or 5. And we can write our final statement. We can say the dimensions. Move this up a bit. The dimensions that maximize volume are w equal to 10, and this was centimeters, so put centimeters, h equal to 5 centimeters. And there you go. Again, the solution to our problem here. You want to find maximum volume, you wouldn't want to find a minimum volume. At least not in this case. Now for homework, there's a couple questions I want you to try. So here we have a box with a square base, and the video is at the min-max Q1. And then here's another question with a rectangular storage container, and you have to deal with the cost. Again, this is Q2. So make sure you try these two for homework and then watch the videos to make sure you got the correct answer, or if you got stuck, to help you out with it. We'll have some more videos next time on some more min-max problems, and eventually we'll get to the min-max worksheet, which is at the end. You're welcome to try that now if you want, but mostly focus on these two questions as we're building our skills and our repertoire with the min-max problems. So we'll look at another few examples next time, but until then, thanks for watching.